This is CS402 on Wednesday, July 9th, 2014.
All right, kernel 2, it has a little more than 1 week. Should be plenty of time to finish. I guess nobody's posting in the class Google group. I hope it's not a bad sign. So anyways, if you're stuck, post to the class Google group, send me email, and proceed like that. If you have code from the previous semester, please don't copy from it, and the best is just to get rid of it. What we have learned in this class certainly is enough for you to do this assignment. So you don't need those code. And again, a reminder, grading guidelines is the only way we will grade. And so read it. There's one major test in kernel 2. It's called VFS test. You should make sure your code pass every one of those tests. Okay? Because when you go into kernel 3, anything that's not correct in kernel 1 and 2, you're going to end up fixing them because otherwise everything's just going to blow up. Okay, so it's sort of very important to make sure your kernel 1 and 2 is done. The code should be in pretty good shape. If you have minor bugs, you can fix it. But if there's some kind of a major thing, like you introduce a new data structure, inside the kernel, then you might be in trouble. Okay, so try to make sure that everything works. Instead of sort of getting around the problem, try to find out where the bugs is and then fix the bugs. All right, so for kernel 2, I guess one thing I want you to pay attention to is to learn how polymorphism work. Okay, and again, polymorphism is a sort of a C++ concept, but there's really no objects, and I guess when you finish chapter 3, you should know that the only thing you have, is data bytes and symbols. Addresses and data. There's nothing else. Okay, so everything else is an illusion. So clearly, you can implement everything in C++ in C. So polymorphism is for it's sort of thinking of things as in objects. So you have an object that's just a pointer that points to this object. Sometimes this object acts as one kind of object, and sometimes acts as something else. Right? So in the world of C, that means that you have a pointer to something. You don't know what it is. And we do that in warm-up number 1, right? It's the void star pointer. Okay? Sometimes you have to interpret this void star pointer as one type of data structure. And then another time, you got to interpret it as another type of data structure. Okay? So that's how polymorphism works in C. In kernel 2, so kernel 2 is virtual file system. You actually, there is a underlying actual file system that's supporting kernel 2. Okay, that actual file system is called the RAM file system, okay, or RAMFS. Okay, so remember that at the system file table, there's one inode object. I guess in VFS it's called vnode, right? So from that point on, you go from the virtual file system to the actual file system. Okay, so you are implementing the virtual file system, and the actual file system for kernel 2 is a RAM file system. So there's no disk. You're using random access memory or memory as your file system. Okay? So see how that code transitions from your virtual file system to the actual file system by walking through the code over here. When you're at GDB, you're at that boundary. step into the code and see what it points to. Okay, so at this point, it's pointing to the RAM file system. When you start working on kernel 3, the first thing you have to do is to switch on the system file system. So you'll be switching from the RAM file system to the system file system. Okay, so the same pointer used to point to the RAM file system now in kernel 3 is going to point to the system file system. And at that point, you don't have the code for the system file system. That's why it's sort of important to understand how things work in the RAM file system. So when you go to the system file system, you can just imagine how the code works because it works exactly the same way as a RAM file system. Okay, the interface needs to be exactly the same, otherwise polymorphism is not going to work. Okay, so make sure you spend some time walking through this code to see what is a file system supposed to look like, at least from the point of view of the virtual file system. All right, so later on we get switched to a different file system, you won't get sort of surprised as, oh, I have no idea how this works. Well, you should know how it works. All right, so even though in the RAM file system, there's no locking because there's no device you have to wait for. If you want to access the RAM disk, well, you don't have to wait for rotational latency or, seek time and things like that. So you get the data right away. That's the main difference. Okay, there's really no blocking in the RAM file system. All right, so make sure you read the code. Another thing that's different about kernel 2 is that you need to learn how reference counting work. Right, we sort of mentioned that in the system file table, one of the entries is a reference count. Every time you reference it, you bump the count, and every time you dereference it, you decrement the count. Right, and when it goes to 0, then you deallocate that kernel resource. Okay, so things in the kernel, many of the resources sort of work like that, and this is where you need to understand how it works. And so even though we have the virtual file system, we also have a reference counting mechanism. So make sure you sort of know when to. I mean, the tricky part is to figure out exactly when to add a reference and when to remove a reference. Okay, don't just blindly do it. Right? I mean, the basic idea is very simple. Here is an object. Okay, if you have something that points to it, well, then the reference count needs to increase by 1. Right? Okay, if this object is destroyed, then whatever it points to, you need to decrement the reference count. That's all. Okay. So don't just add references all over the place. Or if you have a function, if you go in there and you're going to go out right away, and there's no blocking inside your function, well, then you don't really need to have to bump the reference count. Okay? You bump the reference count if you point to it, and this object needs to stay around for a while, and eventually when this object get decremented, and then you need to decrement. Okay? And I guess when you, all right, so anyways, if you, I don't remember exactly. I think if you don't do the reference counting correctly, then later on when you try to shut down kernel 2, it might be the case even that the kernel 2 the kernel will refuse to shut down. Okay, so if you look at the grading guideline, you're going to lose points if sometimes the kernel will not shut down. Okay, so make sure you do the reference counting correctly. Set breakpoint to find out why is this memory object. The reference count doesn't go to 0, and make sure you fix the bug. Okay, so by the way, the kernel refused to halt. All it means is that, if you see this message when you exit the Unix kernel, right, you see that in kernel 1, you see the message in the terminal that prints Unix : halted cleanly, well, that means that the kernel is halted. Okay, so if you can see this, then that means that the kernel has halted. Okay, even though you might get warning messages and stuff like that, that's really not a big deal. Okay, so make sure you can see this one so that the kernel is willing to halt. Or the kernel is happy enough that it's willing to halt. All right, so make sure you get here. All right, okay. And again, if you get into trouble, make sure you send an email and post to the class Google group. All right, so today we're going to talk about what you need for kernel 3. So we skipped part of the chapter 6, right? We only covered the beginning part, enough for you to do kernel 2, and now we're going to get into kernel 3. And today and the 2 lectures next week are very important to your success in kernel 3. Okay, so if you have a question, so I really recommend you that when you're done with the lecture, you can ask question now, and or when you review the lecture, if you're confused, ask me question right away. Okay, so far you should know that the class and the kernel project is really not about just hacking, right? I mean, it's about understanding how everything works, right? These are brand new concepts, and you can see that how do you translate these concepts from what covered in the lecture, right? Even though the lecture stuff isn't really directly related to Unix, but these are high-level concepts that actually you see the implementation in Unix. Okay, so same thing go with the, the kernel 3, is that there are these concepts, we're going to, turn them into code. All right, so it's very important to understand the concept. All right, so chapter 7 is about memory management. So, some people call it just virtual memory, so that's sort of the focus. All right, so the basic picture is like this, right? You have user processes. I guess the line is drawing a little funny. Here is the user processes, and here's the operating system. I guess there should be a line over here. And then, here's the physical memory, right? So down here is the hardware. Okay, over here, this is the application space, or the user space, and here's the kernel space. Okay? So we need to protect the processes from each other, and we sort of mentioned we're going to use the address space concept and things like that. So we're going to see how this is all implemented. Okay, so down here we have the physical memory, and the physical memory is used to support all these activities in user space and in kernel space. So the challenge is that, if you need to run a lot of user processes, you're going to run out of space. So what do you do, and how do you protect things from each other? Okay, so we're going to use the address space concept, right? It protects the processes from one another. It protects the operating system from user. And it turns out that once you start doing this, using this virtual memory, solution to solve the address space problem, then you can use the virtual memory solution to do a lot of other stuff. Okay, it turns out all these things are important things in the kernel. So we're going to go through this and see how these important concepts are implemented using the address space and the virtual memory concept. All right, so first talk about virtual addresses, right? So remember that when we talk about booting, we say in the Linux booting, there are, two parts that are done, I guess there's 3 stages, right? The 2 parts are done in assembly language, and then finally get into the C code. And the C code is where you have process 1 and stuff like that. And our kernel assignment basically start with, the C code, okay? And in the second part, there's a little phrase that says, turn on, virtual memory. Okay, so what it's saying is that, when you first try to boot the operating system, in the beginning, the addresses that are used by the CPU, they're physical addresses. Okay, at some, so at the lower level, when it's trying to set things up, in assembly code, you can deal with physical addresses. But as soon as you start to go into the real operating system, you have to switch to virtual address. Okay, so once you turn on virtual address, then everything is using virtual address. Okay, the operating system that you are doing, they're all using virtual addresses. In kernel 3, you have to implement user processes, and of course, user processes are using virtual address. Okay, so we're going to see, what is the virtual address and who is using them. All right, so over here it says, basically everybody, use, every piece of software, okay, that you will end up touching uses, virtual address. Okay. So you will use, so if you have a 32-bit processor, right, you will use a virtual address to address any memory location in the address space. Okay, so the virtual address is sort of tied to the address space concept. If anything that has an address space, well, you address it using virtual address. Okay, no physical address. Does anything use physical address? Well, yeah, it turns out it's something like this, right? If you have a picture like this, here's the CPU. Okay, and then here's a memory device, a memory, and then here are other devices. They all go connected to this bus. Okay, so when you address the bus, what goes on the bus has to be a physical address. Okay, so if you have memory over here that's, I don't know, half a gigabyte, well, if you try to address the memory, you better not use the complete 32-bit address because, there's no memory there. Okay, so of course we can do memory map I/O. Some of the memory addresses we can map to I/O devices, okay? But what's important, the important message over here is that what goes on the bus are physical addresses, okay? So when the device doing DMA transfer and stuff like that, then it's using, physical address, okay? When your processor is executing instruction, okay, then everything's happened over here inside the processor, okay? So what's come out of the processor is physical address. What's used inside the processor is the virtual address. All right, so when we execute instructions, right, we sort of talk about, Turing machine, how it works and stuff like that, right? You fetch stuff from memory, you go inside the processor, and the processor do stuff with it. So inside the processor, the virtual memory is used. Okay, when you need to go to memory, we need to go through this, translation of translating from the virtual address to physical address. All right? All right, so nothing in the operating system uses physical address, while the hardware uses, physical address. So we need to generate, virtual address, references, right? You need to, generate a memory reference, okay? So if you want to access any kind of a memory location, okay, then you are, generating a memory reference, okay? So in that case, every piece of code that you do, well, you start with a virtual address, and that virtual address get translated into a physical address, okay? So why would you want to access a memory location? Okay, well, it turns out we do it all the time, right? So, for example, I'm going to look at 3 examples, right? When you fetch a machine instruction. Okay, when you fetch a machine instruction, you should use a virtual address or you should use a physical address. Well, over here it says, well, you need to specify a memory location to fetch them. Okay, so this machine instruction is sitting in memory, right? So you need to go there and fetch that instruction, put it into the CPU so you can execute that instruction. Okay, so how do you fetch memory on, how do you know where to go? Well, I mean, in the x86 CPU, the EIP register inside the CPU, okay, tell you where to go. Okay, so in this case, the EIP register contains a virtual address. Okay, so when you fetch a machine instruction, well, that's when you need to go to memory to get it, and the only memory location that you have is a virtual memory location. Okay, so this virtual memory location is stored in EIP. Okay, so it needs to get translated into a physical memory before you can actually go fetch that instruction on the physical memory. Okay, so EIP contains virtual address. What about this? You push EBP onto the stack, right? When do you do that? Remember, every function call, the first thing is push EBP onto the stack, right? Okay. So in that case, EBP is a register inside the CPU. You want to store it onto the stack. Okay, where is the stack? Right, the stack is pointed to by the ESP register. Okay, so again, you have a CPU over here. Okay, I mean, where is the actual stack? Well, the actual stack is in memory, right? Okay, so you need to store the EBP register into this memory location. Okay, but over here, you only have virtual address, and over here, a physical address. So you need to generate a virtual address that gets translated into physical address, so you can store this, 4 bytes into this piece of memory that's going to look like the stack. Sorry. Okay, so you need to specify a memory location to store the content of EBP. Okay, because that's where the stack pointer point to, and then after that, you're going to increment. I guess when you push something on the stack, you're going to decrement the stack pointer by 4. Okay, so how do you know which memory location to write to? Well, you use the ESP register. So the ESP register also contains a virtual address. Okay. What about this guy? X is equal to 1, 2, 3, where X is a local variable. Local variable is on the stack. Okay, but we know that this memory reference, right, when you say X equal to 1, 2, 3, you're generating a memory reference, and you want to store the value of 1, 2, 3 into the location of the address of X. Okay, and again, that's sitting in physical memory somewhere. Okay, but all you know is a virtual memory location. So in this case, where does the virtual address come from? Right? It's a local variable. The memory reference to a local variable is relative to the content of EBP. Okay, so you're going to take EBP, local variable, I guess, again, go back to the stack frame, right? So if you have a address space, here's the stack, and this is the last stack frame. Local variable are sitting right here, and EBP is right here, right? So you're going to take the EBP value, subtract some offset, and that will give you the address of X. Okay, and then you use the X, go through memory, address translation, that will give you a physical address to store, that X. Okay, so therefore EBP also contain a virtual address, right? So ESP contains a virtual address, EBP also ESP, EVP, pretty much everything contains virtual addresses. All right, so who contains physical address? Well, it turns out there's one register in the CPU actually contains physical address. Pretty much everything else is virtual address, right? Because once you are in the, once you finish the booting process, once you got into this, once you got into the C operating system, then everything is virtual address. Okay, remember when you start the operating system, how many processes do you have? You have one, right? Okay, and then everything else is spawned off from that process. Okay, the user process, who spawned off the user process? Right, so again, go back to what we talked about, right? I guess on Nunkey, the guy who started the user process is the login shell, and the login shell is spawned off from the our login daemon, etc. Right? Okay. All right. So the basic idea is that we have to do this address translation, right? It's one level of indirection, and there's a piece of hardware, that's doing this address translation. That's called the memory management unit, or MMU. Okay, so you have this picture. I guess I'm gonna call this core inside the processor. I'm gonna call this the CPU core, right? We have a processor right here. It's a single processor. It has a single core. Some people will call this entire processor the core. Okay, so what I'm talking about is that sort of the internal part of the processor. So this one would generate virtual address. Okay. And then internally, inside the processor, it goes to the memory management unit, which translates the virtual address to the physical address. And the physical address is put on the bus to address physical memory. All right, so when you have multiple core, maybe some people will say, well, multiple core, every one of these core has an MMU inside. But since we're talking about the MMU, we sort of draw the picture like this. So it looks like the MMU is outside of the core. I just want to sort of mention that if you read something else on the internet, if they say MMU is inside the core, that's perfectly fine. Okay, it's just easier to draw it this way. All right, so we can say that, well, here's a core, and here's a virtual address, and here's the physical address. Sorry, here's the virtual address, and here's the physical address. All right, the memory address, so the virtual address is translated into physical address via the MMU. All right, so over here we're going to see an example. We have two user processes. Process A is blue and process B is pink. Both of them wants to use virtual address 100. Okay, so the idea over here is that, this MMU, if you load it with the right kind of information in there, then it will do address translation for the right process. Okay, so if you want to do address translation for the blue process, you better pick blue stuff, put blue stuff over here. If you want to do address translation for the pink stuff, you got to, put the pink stuff over there. Okay, so we're going to end up with something that might look like this. In the physical memory, we have part of the physical memory allocated for the blue process, and part of the physical memory allocated for the red process, pink process. Okay, so when you're running the, the blue process, process A, what the operating system has to do is to make sure that the MMU, there's a bunch of controlling register in the MMU. They have to be loaded with the information that are associated with the blue process. Okay, so from this point on, when you do address translation, if you generate a virtual address 100, okay, then it will be mapped or be translated into the blue region. Okay, if you're running the ping process, okay, the same virtual memory location, 100, in this case, a different set of registers is going to be loaded over here. So now it's going to point to this other part of the memory so that, so this guy can also access location 100, and then automatically it will go to this part of the physical memory. All right, so the operating system job is to make sure that these registers are loaded with the right value. Okay, so when you switch from one process to another, right, how do you switch from one process to another? Right, you can give out CPU, you can get a timer interrupt, right? We talk about, deferred procedure call and things like that. In the operating system, when you switch to run a different user process, you got to make sure that you load the MMU with a different set of register values. All right, because otherwise, when it generates this address reference, it's going to point to the wrong place, and then you lose protection, right? Because then you have one, process, accessing memory of another process. Okay, so the operating system is the guard over here to set all these things up so that address translation will be performing correctly. All right. Okay, so we're going to talk about how all these things are done, right? This is the basic high-level picture. We're going to look at some example of how this is done, and then see how this address translation concept can be used to provide a bunch of features that we have talked about already. Okay, the features that we talked about, memory map files, using large memory, sharing, protection, all these kind of stuff. How is it achieved using this basic, again, it's one level indirection, okay, and it turns out it has a lot of benefits, okay? And what we're going to do is that we're going to sort of first sort of walk down the memory lane and talk about how things are implemented in the old days, because I think it's easier to explain things that way. And then we're going to talk about, how the current memory management works, okay? So we're going to start from sort of the simpler, concept. In the very good old days, there's something called the memory fence, okay? So what happened is that you have the operating system sitting at a certain address, and then above that, you run the user, process, okay? So what happened is that the MMU is just tell you where the memory fence is. Okay, so if you run the user code, if you try to access anything in the kernel, you would generate a fault. Okay, so the picture over here we draw over here is that the MMU is simply a register, it's a hardware register that stores the location of this fence, it's an address of the fence. So if you try to generate a memory location, if it's within the user area range, then it's allowed to translate directly from this address to this address. So there's no translation. Okay, so the code over here, you can access physical memory directly. Okay, if the user program try to access any of the operating system location, then the hardware over here will generate a fault to the CPU, and you trap into the operating system. All right, so this is really straightforward, and this is you can only run one user process at a time. Okay, not very useful, right? We have one operating system, one user process. Okay, and this user process is allowed to do anything over here. I mean, in a way, the good old DOS is kind of like that. Okay, you only run one program at a time. All right. Okay, what if this program is big? It doesn't really fit in this memory, right? In the good old days, the memories are expensive. So what you need to do is that so in the user area, so still the operating system is down here with a fence right here. Okay, if the user program is large, it doesn't really fit in memory. Then what happens is that the programmer are required to split their program into two parts. One is called the resident part of their program, which always stay in memory, and the other part is called overlay. So so the overlay can be actually brought from the disk into this area, when needed. Okay, so if you have a large program, right? Here is the resident part, okay, and then here's overlay 1, overlay 2, overlay 3, overlay 4. Okay, depends on which one you want. You've got to execute code inside the resident area and bring in the right piece of code from the disk onto this area, and then you can, this could be data or this could be code. You can actually make procedure call into the overlay area, and then eventually return back over here, and then you can switch to another overlay. Okay, so this is the good old days, and the programmer actually have to do all that. Okay, I mean, I actually tried to write a program like this, and it was miserable. So programmers should never have to do something like this. Okay, so anyway, so this is ancient. Later on, come with the concept of base and bounds register. Okay, so the idea over here is that in the previous approach, you can only one user process at a time, so it's very limited. So in order to support multiple user process, what happens is that the operating system will maintain a pair of registers for every user process. Okay, and these registers are called the base register and the bound register. Okay. The bound register is basically the size of the address space for the user process. So you have a user process, you add everything together, the code, the data, the stack, and the heap. If it comes up to be, 1 megabytes, then you put the bound register equal to 1 megabytes. Okay? So the bounds tell you how much addressable memory that user process has, right? So which is the address space of that user process. Okay? The base register tell you the start of the physical memory for the user process. Okay, so this case, if you have a larger piece of memory, what you would do is that, if you allocate this one for the blue process, then, the base location of this area is what goes into the base register for the blue process. Okay, so in this example, right, the base register for the blue process is 1200, right? 1200 locations is right here. So starting from here, belong to the blue process, and the address space for the blue process is only 300 memory location. So the bound register tell you that for the blue process, start from 1200 to 1500 minus 1, and that's where the blue process can execute. Okay, so this area contains all the code, all the data, all the heap, all the stack, for that user process. Okay, similarly for the ping process, the ping process is allocated over here. Start at memory location 9300 for 500 bytes. Okay, so therefore the base register is 9300, and the bound register contain 500. All right, so every user process has a pair of these register. So in that case, what happens is that when when the user process is running, then the MMU needs to be loaded with the base and the bound register for that user process. Okay, so in this example, so what happens is that the address for the program and the data, the address are relative to the base register. Okay, so inside this particular user process, the only memory location that it can generate is between 0 and 299. Okay, anything beyond that, you're gonna create a fault. Okay, so what happens is that if the blue process is running, right, so it will generate a memory reference. Okay, it needs to be between 0 and 299. In this case, it generates memory location 100. Okay, so this 100 is like the virtual address for the blue process. Okay, so you need to get translated into physical address in order to access physical memory. Okay, so in this case, the MMU job is to compare the virtual address to see if it's out of bounds or not. That's why it's called a bounds register. Right? So in this case, you compare 100 against 300. 100 is less than 300, it's okay. It's allowed to proceed. And the next thing that you do is that you take the virtual address and you add it to the base register, and that will give you a memory location. Okay, so in this case, 100 plus 1200 will give you 1300. You end up accessing this memory location, and of course, that one is in the blue region. All right, so I guess this basic concept, we're gonna talk about all the the virtual memory, the address space feature using this concept of base and bound register. Okay, so please make sure you sort of understand this slide. All right, so in this case, right, the virtual address is this address, the physical address is this address. Okay, and inside over here, we perform the address translation inside the MMU by first checking if the virtual address is within the bounds, and then if it is, then we add the virtual address to the base register, and then we get the physical address. Okay, so the address translation is done just by adding the virtual address with the base register. Okay, so later on, other scheme might be a little different, but that's sort of the basic concept. Okay, and the memory reference has to be between 0 and bounds. Okay, so this for the blue process, you can actually allocate memory for the blue process in physical memory. You can allocate it anywhere. Okay, I can put this code right here, put this code right here. It doesn't really matter where I put it. As long as I point the register, the base register at the right place, then I don't need to recompile the code for the blue process. Right, because the blue process uses virtual address, always go from 0 to 299. Okay, so you can locate this piece of blue memory anywhere in physical memory, and it's all gonna work. Okay, so this is known as position independence. All right, that the code that I compiled over here doesn't really matter where I put in physical memory; they will execute exactly the same way. Okay, so the base and bound register is actually a pretty powerful concept. It allows you to compile this code, independent of how address space is allocated or how physical memory is allocated for the user process. If you, run the ping process, right? The ping process, the error is right here, and the base register is 9300. The bounds is 500. This example, they generate virtual address 100. Okay, so over here, we better make sure that in the MMU, the base and the bound register are loaded with the right value. Okay, so in this case, you compare 100 against 500. It's less than 500. Address translation is allowed to proceed. You add 100 to the base register. You get 9400, and 9400, you access this memory location. It belongs to the ping process, so everything is okay. All right? Okay, so it's kind of not really good to put the code segment together with the data segment, with the heap and the stack. And one of the main reasons is because the code segment is different from all the other segments, right? The code segment is read-only, while the other segments are not. Okay, so it's a good idea to separate these segments. Okay, so the next step beyond base and bound is what's called segmentation. Okay, so segmentation is basically the same idea as the base and bound register, except that you have multiple segments now. Okay, and every segment gets a pair of base and bound register. Okay, so if you have one process, you're going to have 4 pairs of base and bound register, one for the text segment, one for the data segment, one for the heap segment, one for the stack segment, or how many segments you can have depends on your CPU architecture. Okay, so every different segment get a different pair of base and bound register. Okay, so over here, I can have this example in my address space. Okay, so I actually intentionally create some holes over here. The code segment go from virtual address 0 to 200. The data segment goes from 300 to 400. The heap segment goes from 600 to 1600. And the stack segment goes from 2000 to 5600. Okay, so therefore that will tell you what the bound register has to be, right? For the code segment, the bound register is 200 minus 0, right? So the bound register is right here, 200. For the data segment, the bound register is 400 minus 300, so it's 100 right here. For the heap segment, 1600 minus 600, it's 1000. And for the stack segment, it's 5600 minus 2000, so it's 3600. Okay, so this is the base register, this is the bound register, both are B. So this is the base, this is the bounds register. Okay, so now you have 4 pairs inside the MMU. Okay, and then each one of them is mapped to a different place, in the physical memory. And then this mapping can be location independent, right? So these segments, when they map to physical memory, they can go anywhere inside physical memory. All you need to do is to have the base register point to the right place. Okay, so in this example, the code segment is allocated at location 9000. Okay, and then the next 200 bytes belong to the code segment, right? So 900 goes here, and again, we have 200 here. Okay, for the data segment, it was allocated right here, 10300. It's right here, right? So it points to the base. And for the heap segment, it's allocated right here, 2200. And for the stack segment, it's allocated 5800. Okay, so this picture is sort of related to that picture. Okay, and now when you generate a memory location, right, the compiler sort of know that, when you generate a memory location, whether it's generating a memory reference because of the, the code segment or the data segment or the heap segment and stack segment. So, the address that gets generated over here, you can actually tell, which segment it belongs to. Okay, so we're going to sort of draw this picture. So again, this picture, it's sort of, I drew this picture to explain these concepts. They might not match any, previously existed, hardware architecture. Okay, so we're going to sort of stick to, this particular way of using, segmentation. All right, so it's segmentation because memory is segmented into these, 4 different regions. Okay, it might not, correspond to any physical processor that was used in the 70s or something like that, but so sort of bear with this kind of notation. All right, so we're going to use this weird things where the CPU know exactly which segment it's using. Okay, so in that case, when it generates a virtual address, it tells you which segment that it's using, and also they tell you which offset it's generating the access for. Okay, so in this case, I'm going to access data segment, with an offset of 50. Okay, which means that the original, virtual address is going to be 350, right? Because the data segment is right here. The actual original virtual address is going to be 350. Okay, so the picture I use over here is that when it's coming out of the core, you already know which segment it's addressing and what is the offset into that segment. Okay, so this is just, the way I represent this, right? So this way you know which pair of base and bound register to use right away, because the data segment, I know I need to use this pair, okay? And then what I will do is exactly what I did before, right? Once you narrow it down to a pair of base and bound register, well, then we know what to do, okay? We'll compare this address with the bound register to see if it's less than the bounds. If it's less than the bounds, then address translation proceed. If it's bigger than the bounds, then you generate a fault. Right, so over here, we're going to do comparison, and then if it's a faulty, memory reference, you generate a fault. okay? And if it's less than the bounds, then you take this offset, right? This is the offset within that segment. You take this address, you add it to the base register, and that will give you the physical memory address. Okay, so in this case, 50 add 1 plus 10300 is going to give you an address reference right here. All right, and this one is a data segment. All right, so please, remember that this is the notation we're going to use. From the core, we don't really use original, a virtual address. We're going to, map it over here to determine which segment it belongs and generate an offset into that segment. Okay? I think there actually a processor that you sort of used to do that, but of course those processors doesn't exist anymore. All right. Okay, so that's the basic idea, right, with segmentation. Okay, and now, and again, the reason we want to do this is we want to protect the the program so that it's read only. Okay, so what do you have to do, right? So what needs to be done is to separate these memory segments, make sure that some of them are rewritable and some segments are read only. Okay, so where do you store that information? Okay, so in this picture, it shows you that it stores that information inside the MMU. Okay, so inside the MMU, for every segment, you gotta have the access control or the protection bits for that memory segment. So in this case, our code segment is read-only, our data segment is read-write, and then the heap segment is read-write, and then the stack segment is read-write. Okay, so in that case, if we need to write to virtual address 150, okay, so in this case, we have code segment right here, 150. Is the offset. We compare 150 against 200, it's below it, right? So therefore, we are allowed to do address translation. But then it will realize that this is a read-only segment, and you try to perform a write operation to it, and that's when a fault is going to get generated. Okay, so the fault can be generated because, the offset is out of bounds, or in this case, it could be, it's an access violation. All right? So in either case, what you're generating is a segmentation fault. Right, so this is where the segmentation fault name comes from. Is whenever this guy, you generate a fault into the core, that's called a segmentation fault. Okay, so once you start doing that, okay, you can actually allow a segment to be shared. Okay, so if I have two user processes, process A and B, right? So now I can actually have them both share the same segment in physical memory. Okay, so both of these two processes, maybe they're running the same program to start with. So therefore, I'm only going to have one memory image inside physical memory. So what I can do is I can allocate this piece of memory, and I can have it shared. Okay, so the way I'm going to do this is to have both of them to have the same base and bound register. Okay, and make sure that they're both, read-only. Right, so in this case, no matter whether you're running the blue process or the pink process, when you execute code, they will all be translated into the same memory location. Okay, so in this case, the blue process, right, all the other segments will map to different places in memory, and the pink process will map to different places in memory. But when it comes to the code segment, the base register are both pointing to 9,000, and the bound register are both, being 200. So in this case, if the blue is running, right, this will point, right here, and if the pink is running, okay, and again, this part point to exactly the same place, so therefore, it's okay to share them this way. Okay, and also in this case, right, the memory protection is very important, okay, because you don't want one process to modify the code for another process. Right, so if you don't have this, memory protection over here, you're going to end up with one process changing the program for the other process, and the other process is not going to be very happy. Okay, so therefore, this access protection is very crucial when it comes to sharing memory segments. All right, so segmentation fault, right? So the general concept of segmentation fault, anytime any kind of a comparison failed, you will, generate a fault into the core and then trap into the operating system. Okay, so this fault could be the case where the address does not compare, or could be the access, you have access violation, or any kind of things that not supposed to do, you're going to end up generating a fault and then send the CPU. So right now the CPU is executing the blue user process. as soon as the fault is generated, it will trap into the operating system, and the operating system is going to look at what's generating the fault, okay, and decide what to do. All right? Okay, so with this basic scheme, again, we're still in segmentation. We can actually also implement memory map file. Okay, memory map file, we mentioned that there's a system called mmap. Okay, so you can map a portion of file into memory, and this is the way to do block I/O, right? Okay, so we're not doing sequential I/O. If you want to do block I/O, you can map the entire file into the address space, or map only part of that file into the address space. Okay, so over here, here's a file. Okay, if you want to map it to the address space, if you want to map the entire file into the address space, we look at how big this file is. Okay, so this file, in this case, well, actually we're not mapping part of it. This file, let's say that this file is 820 bytes long, right? 8820 minus 8000, that's 820 bytes long. Okay, we're going to map the entire file into the address space, but we're only going to bring in a portion of it to work with. Okay, so in that case, well, actually over here, the bounds is 820. Okay, so sorry, we're mapping the entire file into memory. Okay, so what happens is that we can allocate a physical memory. This one is 820 bytes. Okay, to map the entire file into memory, basically copying the entire content into this memory segment. Okay, so in that case, what we need to do is that what segment register do we use? Well, it turns out we run out. We don't have a segment register. We only have code, data, heap, and stack. So in this case, we need the fifth, segment register. Okay, a base and a bound for that, for the segment. So in this case, in order for us to use memory map file, we actually have to allow the flexibility of using additional base and bound register. Okay, so this is the newer processor, has more than 4 pair base and bound registers. So maybe this processor has 16 of them, where 12 of them can be used for memory map files. Okay, so in that case, you're going to allocate one of these 12 registers for the memory map file. Okay, and then in this case, we're going to map this one to this memory location. So therefore, the bounds for the entire file is going to be 820, and the base register will point to where the beginning of this address is. All right. So in this case, when you generate a memory reference over here inside the CPU, you need to again subtract these two guys, A1, A7 minus the virtual address for this memory map file, 8000. You're going to get an offset into offset equal to 178. And then this one says I'm going to use the memory map file 1 register, that segment register. So therefore, the 178 is going to be compared against 820. If it's less, then the address translation allowed to go on. So you're going to get 178, add to 400, and the memory reference that you're going to generate over here, I guess it comes back here, and that's the memory location you're going to reference. All right, so again, the memory map file concept is to do block I/O. Right, so you map this thing into address space. So if you want to read files, all you have to do is to read from memory directly. If you want to write to the file, you modify, that file by writing to this memory location. And eventually, when you're done, you close the file. This data get copied back to the disk. Okay, and then things get updated that way. All right. So in this case, right, this segment is rewrite. Okay, so that. What about if you have another process, if you want to share the same file, can you do it? Right, so similar to the read-only segment, you have a second process, the ping process. They also want to use the memory map file. So then you have to be careful, right, whether these two processes are allowed to share that file or not. Okay, if they're allowed to share that file, then you can use the same trick as the text segment, have them all point to the same place. Okay, so in this case, process A and process B can both modify memory over here, even, interleave each other, and then eventually when they all close the file, then the data go back onto the disk. All right? It's a little dangerous, okay, but it can be done, right? All right, you can also implement copy on write using the scheme. Okay, remember what's copy on write, right? Copy on write is that, when the process first start using a piece of memory, okay, so that one is kind of read-only. And as soon as when you try to write to that memory segment for the first time, you make a copy and you write to the copy. Right? So again, a process gets a private copy of a page, or in this case, it's going to be a segment. Okay, I actually copy this this line from a few chapters ago, right? Over here it says page, but in this case we're talking about segment. Gets a private copy of the segment after a thread in the process perform a write for the first time. Okay, so as long as you're reading it, you get the original copy. When you write to it for the first time, you got to make a copy. Okay, so for example, if we have this case, you have a virtual address trying to read 312. 312 is offset 12 into the data segment, right? So data segment number 12, you're going to use this. 12 is less than 100. Okay, so address translation is going to happen over here. Okay, but this case, we are performing copy on write. Okay, so the way that we're going to do copy on write is first, this memory segment, even though it's a data segment, you're supposed to be able to write to it. Okay, but since we're doing copy on write, the operating system has to get in the middle. Okay, how do we make sure the operating system get in the middle? Well, by generating a fault, right? Because if you never generate a fault, this user process is going to continue to execute in the CPU without interruption. Okay, so remember, if your operating system usually is not doing anything, right? It's sitting there waiting for something to happen. Okay, so in this case, it's waiting for a trap to happen. So in order for copy on write, that magic to work, you have to go into the kernel. Okay, so you have to force a fault. Okay, so the way we're going to force this fault is to make this memory segment read-only. All right, so we're going to set this guy read-only. So when you write to it, over here we're still doing read. Read is okay. I guess the next page we're going to write to it. Okay, so again, when we try to read to it, read from it, okay, 12 is less than 100. You generate this memory reference. You go there and read. Right, everything is fine. Okay, over here we're going to introduce an extra flag over here. Okay, so we're going to introduce another bit into the MMU. Okay, so for every segment, we're going to add another bit. This one says whether this segment is private or shared. Okay, so when we talked about previously, the code segment, you want to share it, so that bit will be say shared. If you have a memory map file and that file is shared, then that bit will be shared. Okay, but now if you want to implement copy on write, we got to do this and we got to set this bit to private. Okay, because again of the sentence, right? A process gets a private copy of a segment, okay, after a thread in the process perform a write for the first time. Okay, so what you're doing over here is to declare that this segment that I pointed right here, this one is supposed to be private. Okay, so what we're going to do is going to make it read only in the beginning. When you try to write to it for the first time, you generate a fault, and then you can get a private copy. Okay, so let's see what happens when we try to write to the segment, right? If you want to write to the segment, 312 is offset 12 for the data segment. You're going to come over here. 12 is less than 100. That's okay. Okay, but you're going to generate a fault because you try to write to a read-only segment. Okay, you generate a fault into the core, and now you trap into the operating system. Right, the operating system is going to look and say, well, how did I get here? Okay, who summoned me, to get here? Okay, so what it needs to do is it needs to figure out, why did the trap happen? Okay, so it's going to walk down a bunch of data structure, and eventually it's going to realize that, hey, you generate this memory reference, it's producing all this kind of mapping, and eventually you're trying to access a private segment. Okay, and this private segment is read-only. Those two things together, it's an indication to the operating system that this is copy on write. All right, so those two combinations, read-only and private, and you try to write to it, that's a signal to the operating system that you want copy on write. Okay, so, but again, who wants copy on write? Did the user want copy on write? No, the user doesn't want copy on write. It's the operating system want copy on write. Right, so what happened is that before this user process start running, the operating system set up all these hints so that later on, when it gets summoned, when you get trapped into the operating system, it will look at the hint that it places into the MMU to say that, I set this guy up because I want to do, the operating system, wants to do copy on write. Okay, so these are the signals the operating system left for itself so that later on, when you get a segmentation fault, it can see that this segmentation fault is set up by the operating system so that the operating system at this point can perform copy on write. All right? Okay, so in this case, what will the operating system do? Right? It's copy on write. It will have to make a copy, right? So it will go through this address, know where this address is pointed to, make a copy of it, right? It take, in this case, the bounds is 100. So here's 100 bytes. It's going to allocate a segment inside the physical memory and then copy the entire content over here, okay? And then it will adjust the MMU register to point to the right place. Okay, so what happened at this point, it will point 600, so this new memory location is 600, so it will change the base register to 600 and it points to this, and it will also change the protection of this page is read-write. Okay, why is it not read-only? Because it doesn't want copy on write anymore, right? Because you are pointing to the copy, okay? So at this point, this data and this data is exactly the same, right? Because all the operating system did was to make a copy. All right, so at this point, after everything is fixed up, the operating system will return to the user process, and the user process will restart that memory reference. Okay, so there are different kinds of fault. This is the kind of fault where the user, the CPU knows that when this kind of fault happens, then when it goes back to the user process, the instruction pointer was not incremented. It will actually stay where it is, and it will reissue that memory reference, and that memory reference is right to virtual address 312. Okay, and then we're going to start all over again, right? 312 compared to this is offset 12 in the data segment, right? Data segment over here, 12 is less than 100, and write and rewrite over here, voila, it's allowed to proceed. Okay, this time, the second time when it restarts this memory reference, it should not get a fault anymore. Okay, and then it will add 12 to 600, not the previous value, right? It will add 12 to the 600, and then write to memory location 612. Okay, so as soon as the user process restart this memory reference, when that instruction finishes, then this copy will be different from the original copy at that one memory location. Okay? Before that, that segment is a complete copy of the previous segment. It's exactly the same. Okay? So in this case, did we accomplish copy on write? Right? This segment was the original one. Did it get modified? No, it's intact, right? Okay, so actually this memory segment, can I have multiple user processes share that memory segment? I can have them share it, right? Okay, so if many of the, your user program are running LS, okay, the LS, the code segment, we know how to share. Can we share the data segment? Right, the data segment, where did the data segment come from? It comes from the LS executable sitting on disk, right? So all you have to do is to point using a memory map file to point to that page on disk, okay? And now we set up for copy on write, so there's only one copy of that data in physical memory, okay? Once any user process try to modify the data segment, change a global variable, then copy on write is going to kick in. That user process is going to get a private copy of the data segment, and then it can modify its private copy. Okay, so you still might have 100 user processes still sharing the same data segment and sharing the same data segment and the code segment. As long as they don't modify it, they can still share the original data segment. Okay, it's just that when your process try to write to it for the first time, then this will happen. So why do you want to do that? Right, and the reason is to save memory, right? Because why do you want 100 copy of the same data segment sitting in memory? Okay, because we have a lot of user processes, they're all running LS. Okay, this way you can share the code segment and also share the data segment, provided you don't change them. If you want to change them, then you get a copy. All right? So this not only can be done on the data segment, can it be done on the stack segment? Right, the stack segment in the beginning, the stack could be completely filled with 0. Okay, so you can actually have a page inside over here filled with 0. Okay, and also use copy on write. So initially, anybody who wants a page that's full of 0, you just point to that. Okay, you can read from it all you want, you get zeros. But as soon as you write to it for the first time, you set it up to be exactly like this. Okay, so everybody get a separate copy, and that could be the heap, that could be the stack, that could be everything. Okay, so the entire address space, other than the code and the data segment, even the BSS, you can have a separate, segment for it. Then, they can use copy on write. So you have many, many user processes that can share all these physical memory, okay, without stepping to each other's toes. All right? the operating system is playing a very important role, so you got to make sure that you get into the operating system to have the operating system perform all these illusion, okay, that each one of these user process, they all have their own copy of the address space. All right, but in fact, they're actually sharing stuff. Okay? Also, the other thing that happened with the segment is that the segment gets copied, get moved around, all kinds of crazy stuff happening in the operating system. The user process, does it have a clue? No, right? You know, you try to access memory, you know, and then you trap into the operating system, and you come back, you restart the operation as if nothing has happened. Okay, even though tons of stuff has happened, when you trap into the operating system is juggling all these data structure, allocating physical memory, doing stuff on the disk, you know, if it has to, you know, all these kind of things. And then eventually we return to the user process, and the user process says nothing has happened. All right, in reality, tons of stuff has happened. All right, so that's copy on write. And then the other thing that you can do with, you know, the same trick is to have sort of a swap space, or, you know, some people call this the backing store. Okay, so the idea over here is that, you know, if you're starting to run a lot of user processes, you're going to be running out of physical memory. Okay, so how do you allow more user processes to run? Okay, so some of the memory segment, maybe you have a user process that are blocked on I/O for a long time for some reason. Okay, is there any reason that you have a user process blocked on I/O for a long time? Right, I mean, if you want to read from the internet, it can take a long time, right? So therefore, you have a user process basically idling, waiting for data to come from the internet. It's been sitting there for, you know, how long do you wait for the internet? 30 seconds? Okay, so sometimes you can wait 30 seconds at a time. The internet sort of has a heartbeat of like 30 seconds, you know, so, you know, every 30 seconds go boom, boom. Well, it doesn't really do that. But the idea over here is that you can get blocked for 30 seconds if you try to read from the internet. Okay, so therefore, should we, you know, put that process to sleep? I mean, it's not doing anything useful. Why is it using up all this memory space? Okay, so the idea over here, that entire process, or just part of it, can be moved to the disk to put to sleep, and later on can be brought in. Right, so that's called swapping. Okay, so you can swap out one segment to the disk, and later on, when you need to run that process again, you can read it back. Okay, so over here, this picture, right, show you that, you know, here is a segment, right? In this case, it's a heap segment. Okay, you can actually swap it out onto the disk. Okay, so what happens is that this memory is gone. Okay, and then the operating system can allocate this memory for another user process. Okay, so in that case, this will go onto the disk. Who's going to keep track of it? I mean, obviously, the operating system has to keep track of it, right? Okay, so the idea over here, okay, is that the way that you keep track of it, the operating system over here is keep track that this segment for this user process, now it's actually sitting on disk. Okay, it's not pointing to anything in physical memory. Okay, so how do you say that? Well, you introduce another bit in the MMU, and this one is called the validity bit. Okay, I'm running out of space over here, so I'm not still drawing all the other stuff, the private, the share, the read-only, the rewrite. Okay, there is a validity bit over here. Okay, if validity bit equal to 1, that means that this register contains a valid translation. Okay, so if you generate a memory reference, you got to compare against the bound, and you got to add the offset to the base register to generate a memory reference. Okay, if the validity bit equal to 0, saying that this information over here is invalid. Okay, so I don't really care what's in here because it's invalid. Okay, so if you want to access this memory location that corresponds to this reference, this register, then you're going to generate a fault. You trap into the operating system. The operating system says, what should I do? All right, so in this case, what it will do is that it will read, it will try to find out what goes in, what went in here. And in this case, it will say, oh, wow, that particular register is invalid. Okay, so that will trigger the operating system to look for this relationship that maps this segment into the disk, and then what it will do is it will start a disk operation, read that segment into memory. Okay, where would it put in memory? Well, you know, maybe the memory is again out of space, so you have to put something else onto the disk in order to create space for, you know, for this guy. Okay, so eventually you're going to find some place in memory which will be a different place for what it was before. That's why we don't really care what was here before anymore. Okay, so in this case, what we will do is that we will allocate a space and, you know, bring this segment into memory, right? So that operation is called swapping in. Okay, so we can swap that segment into memory, and we're going to find a location for it. And this time, the new location for that segment, right, it's going to be a location 1000. Okay, and this thing is still 1000 bytes, right? So therefore, once we've done this, we allocate a space in physical memory for it and read the data back in here. We got to adjust the MMU register, right? In this case, the bounds is the size of this segment, which is what it was before. The base, we got a new base, okay? But now this is a valid pointer, right? Because the base register and the bound register have valid values. Okay? And again, we're going to return back into the user process. All right, when we return back to the user process is going to restart that memory reference. In this case, the memory reference is going to go through, and it's going to point to a different place, but that's okay. Okay, because you're going to access the correct memory location. Okay, so what happened to the operating system over here that maintains the link? Well, actually, it's still there. Okay. So in that case, anytime if I decide to swap out this segment, it will go to the same place on the disk. All right. So in that case, what the terminology is that this space on disk is the backing store of this segment. Okay. Whenever you want to swap out this segment, it always go to this place on disk. Right. Why does it always go to the same place? Well, because when you try to find place on disk, it's going to take you time. Right. So once you find one place, you want to remember it, so then you don't have to look for that place in the future. Okay, so once you perform this operation once, you remember. So this place on disk becomes the backing store of this segment. All right? So actually, since you want to be able to swap out the entire process, okay, every segment needs a backing store, right? Okay, does this segment need a backing store? Yeah, sure, right? Because it might get swap out. What about this segment, data segment? Well, the data segment doesn't need a backing store. Well, it depends on whether copy on write has been performed or not, right? If the copy on write has not been performed, then this guy will point to the original segment that you read from the disk. Okay, in that case, where's the backing store? Well, the backing store is the disk where the file is stored, right? Because in case you have to swap it out, all you have to do is to deallocate this memory right here, and then you're done. Because you know where this block come from. This block come from that file, /bin/ls, the memory segment, the data segment in that file, in that executable file. Okay, so therefore, you don't need a backing store because you already have one. What about if you have performed a copy on write? If you have performed a copy on write, then the memory segment that you point to, this is going to be a copy with some modification on it already. Okay, so therefore, in that case, this guy need to go to a different place on disk. All right, so for the code segment and the original data segment, okay, they already have a backing store, which is the executable file. For all the other segments, these other segments, and including the stuff that you have already performed copy on write. Okay, I sort of mentioned that name before. So this is called once you have performed copy on write, then this is going to be an anonymous object. Okay, the anonymous object, right? In this case, you started out with a copy of the data segment. Okay, there are other anonymous objects like the pages of 0, right? If you have a page that's full of 0. Okay, again, when you're doing copy on write, well, it's a page of 0, so you don't really need a backing store for it. Okay, but this one represents the stack segment, the heap segment. So when you modify it for the first time, once you modify it for the first time, then it sort of looks just like this one, right? So therefore, in that case, you need a backing store for it. All right, so again, pretty much everything needs a backing store. Okay, so the entire file, entire address space, there are places to go on the disk in case the entire process has to be swapped out. Okay, so part of the operating system job is also to manage the backing store. All right, so this way all the user process can be put onto disk if you have to. All right, so we saw this picture before, right? This is what the address space looked like, okay? And so there are, different segments, right? I guess we said, well, in the process control block, it has an address space representation, okay? So this address space represents, so what is this address space? Well, the address space is the memory map, is the base and bound register, right? It's all these information. Okay, so this is sort of the beginning of a data structure that keeps track of, what does it keep track of? It keeps track of all this picture. Okay, when you trap into the operating system needs to look up these data structure in order to determine what to do. Okay, so therefore it needs a bunch of data structure over here to keep track of all that. Okay, so everything that it puts into the MMU, you need to remember, what did I put in the MMU? Okay, so all that information is stored inside some operating system data structure. Okay, some of them are directly reachable from the process control block, and some of them you have to follow some pointer in order to get to those data structures. Okay, so this picture that's right here, okay, when the operating system needs to keep track of it, it uses data structure like this. Okay, so this represents what the text segment. This represents the data segment, right? And then here's the memory map file. Okay, and here's the stack segment. So maybe this is BSS plus heap or something like that, right? This picture, it tells you where the data come from. Okay, so the text segment and the original data segment. This one tells you which file to come from. What is the file offset for getting the data segment and also the code segment? So you can just read the whole thing in, from the disk. Okay. This memory map file, again, you need to keep using a file object to keep track of which file is mapped to, because this one is using the mmap system call. So you need to keep track of where the file come from and what is the beginning offset, what is the end offset, in case you want to map only part of that file. Okay, and the heap and the stack, originally they point to anonymous objects of page of 0, and they're also done using copy on write. When you modify it for the first time, then you get a copy and you start modifying into the copy. All right, and same thing over here, the AS region that points to the data segment. As long as you don't modify it, then this is the right place to go in case this thing gets swapped out. But as soon as you modify it, then that particular thing is going to be kept track by an anonymous object by first copying the segment from the data segment into that anonymous object, and then all the modification will be done on the copy. All right. So, and we sort of mentioned before, right? Inside this, this address space region, we have, the base and the bounds information over here, right? Here's the base. Well, actually, this is not the base and bound register. This is in the virtual memory. Where does it start and where does it end? Okay, so this one go from 0 to 7 FFF. This one go from 8,000 to 1 AFF, etc. Okay, so it needs to know the size of each segment. And then the access privilege, whether it's read-only, a rewrite and stuff like that, whether it's shared or it's private, okay, all that information is kept right here. Okay, so this way, when you trap in the operating system, the first thing that you need to do is to walk down this data structure, find out which virtual address is causing the fault, and then try to find out what's supposed to happen in that case and see if there's a match, okay? If what's supposed to happen, then you have to perform your logic, your magic of doing copy on write and things like that, okay? Or checking the validity bit, or like, all that business. But if it turns out it's not one of these, operations that's supposed to happen, then it's a, access violation, and then you kill the user process. All right, so you sort of kill the user process once you know that it's not one of these things that the operating system set up for itself so that it can handle all these things, for the user process. All right? All right, so this is the representation for this address space. Okay, so every user over here, right, every user page needs a corresponding disk image, okay, in case the user process needs to be swapped out, okay? What about the kernel? Okay, are you allowed to swap out part of the kernel? Well, why not? Right? I mean, if you're very careful, you can actually do it, right? Because the kernel also uses virtual addresses, so it has its own page table, so you can actually, they also have used the MMU, so you can do exactly the same trick. Okay, but clearly there are some of the things that should never be swapped out. Right? For example, the code that's actually swapping things in and out, that code you better not swap it out, right? Because otherwise, who's going to swap out? Who's going to bring that page back? Okay, so some kernel memory pages or segments, okay, they can be locked down to prevent it from being swapped out. Okay, so some very important, code, like the page out daemon, those kind of code, you shouldn't really swap it out. Okay, so there's actually a way for them to be locked down. So for all these segments, you can actually have a bit there to say whether this bit, the segment, is locked down or not. Okay, if that page is locked down, then it's not a candidate for swapping out onto the disk. Okay, if the lockdown bit is equal to false, then you're free to, even if it's kernel memory, you can actually swap it out to disk because you know how to bring it back. All right. In Unix, it's a little different. Unix is a very simple operating system. Okay, anytime you get a, sort of a page fault inside the kernel, that's a no-no. You should treat it as a, like in warm-up 1 and 2, you get a segmentation fault. It's not supposed to happen. All right? Only when you're accessing user-level code, then, again, this is for kernel 3, when you're accessing user-level code, you can get a fault and get trapped into the kernel, and the kernel can decide what to do. But once you're inside the kernel, you should never get a, get a fault like that. All right? So, I mean, if that happens, that means that you corrupt the kernel memory, or something bad happens, memory allocation chain. So then you need to find the bug. Okay, then it becomes really difficult to find the bug because you're inside the kernel and these bad things happen. All right, so now we're going to transition into what the current virtual memory system look like, because we don't use segmentation anymore. We use paging, right? That's why some of these words that I used in those slides, we're using the word page instead of segments, because the modern system, we don't do segmentation anymore. We only do paging. All right, so segmentation is old. Okay, so even though all the explanation that I used was using segmentation, because you only have a few registers you have to think about. Okay, now when we go to paging, then you're going to end up with a lot of stuff. Okay, so we're going to make this transition into paging. So what is paging, right? Paging is you start with dividing the address space into fixed size pages. Okay, so here's our address space, virtual address space. Okay, we're going to divide them into equal size pages. Typically, this one, typically that means Intel does it because Intel is typical, I guess. It's 4 kilobytes pages. Okay, and you do memory protection based on pages, not segments. Okay, so if in the good old days, right, we have a text segment. The text segment might span multiple pages, right? And then we're going to start data segment right here. Go over here, okay? And then the heap, the stack, and stuff like that. Okay, so we sort of lose the idea that there are these these segments in the hardware. Okay, so the hardware is performing paging. Okay, but the operating system like to think of things as segments, right? Because this picture is what the operating system uses. Okay, the operating system doesn't really like to keep track of pages. It still like to keep track of, segments. Why do that? Right, because then this list will be short, right? Okay, you have, text segment, data segment, whatever, then you're done. Okay, if you have to keep track of pages, if every page is 4 kilobytes, you have 32-bit, so you're going to get 1 million pages. Okay, so you don't want this linked list to be 1 million, entries long, right? Because then, operating system will be really, really slow. Every time you type in the operating system, you're going to do a linear search, and that will take you forever, right? Well, you can use trees to speed up the search process, but still, that's a lot of work. Okay, so we try to keep the address space representation simple by keeping track of segments, but with the understanding that modern hardware uses paging. Okay, so there's a mapping between what the data structure uses in the operating system to what the hardware uses. All right, so we're going to map fixed size pages into physical memory. Okay, so there's virtual address. The virtual address is divided into pages. Physical memory, we're also going to divide into pages. Okay, and the page size is going to be the same. Okay, so here's physical memory. Okay, we're going to divide into 4 kilobytes pages, and this is page 0, page 1, page 2, etc. Okay, so one thing that immediately is apparent is that the base register, for a particular segment that we talked about before, the base register, all they have to do is to point to a page number, in the physical memory. Okay, because the base, the base register always point to the beginning of a page. Okay, and then you add offset into that page. Right, so therefore, all we need to do actually is to store the page number and not the actual physical address for a particular physical page. Okay, so therefore, what we need to store is the physical page number. Page number 3, meaning that you're pointing to the page starts at 4 kilobytes multiplied by 3, all the way to 4 kilobytes multiplied by 4 minus 1. That will give you the last location of this page. Okay. And in order to keep track of these things, you need data structure, right? Just like memory allocation, if you need to keep track of memory pages, you got to put additional information into the data structure, okay? So we can't really, use data structure in physical memory, okay? So therefore, we're going to create these data structure, and these data structure is going to be called page frames, okay? The page frame is, I guess, if you think of it as like, here's a 4 kilobytes page. Okay, we're going to put it inside of a frame, right, like a photo frame, right? This is the page frame. Okay, so every page frame enclosed in it, conceptually, is a 4 kilobyte page. So how do you enclose a page inside a page frame? Well, you have a pointer that points to, or you have a number of the physical page number that remembered by this page frame object. Okay, so this is just a number that tells you which 4 kilobytes, a page is this page frame keeping track of. Okay, so if you have a 32-bit address, okay, then there's 1 million of these guys, or 1024 times 1024 of them. Okay, so all you have to do is to remember which one it is by keeping the physical page number inside the page frame object. Okay, and the page frame object is the object that the operating system used to try to reason about a physical page. Okay, the operating system doesn't really, again, I talked about this before, right? The operating system doesn't really know where the physical page is. Okay, the hardware abstraction layer, when it finished, booting, when it finished power on self-test, it says, yeah, I think there's so much memory. Okay, and it passed that information to the operating system. The operating system just says that, well, okay, that's the memory I have. Okay, the operating system can't feel it. Okay, so they have to take the word for it from the hardware abstraction layer that there's so much memory. Okay, and then it just allocated the memory by using the page frame object to keep track of all the physical memory that it is allocating. All right, so the page frame data structure is used to maintain information about physical pages and their association with important kernel data structure. Okay, so there's a lot of stuff over here inside the page frame object. Okay. So the page frame object, so therefore the page frame contains a physical page number. Okay, so it's not an address, it's just a number, right? If you want to get to a sort of a physical page, all you have to do is to add 12 zeros after it, then you get a physical address, right? Because all these things will start at the base address of a page, 4 kilobytes, that takes 12 bits. Okay, so therefore this address corresponding to something followed by 12 zeros. Okay, so therefore it's really easy to go from a physical page number to a physical address. All right? All right, so there's one-to-one mapping, right? Every physical page is mapped to a page frame object, and vice versa. Every page frame object mapped to a physical page. Okay, so there's a one-to-one mapping between page frames and physical pages. Okay, so therefore in the in the chapter 7 lecture slides, or even in the textbook, sometimes the term physical page and a page frame are used interchangeably. Okay, so when you read the textbook, be very careful. Think about the context. When it says page frame, well, it actually means a physical page. Okay, because there's a one-to-one mapping, so there's really no confusion whether you're talking about something physical or you're talking about the data structure inside the operating system. All right, we use page frame and physical page interchangeably sometimes. All right, that's sort of the normal terminology when people talk about the operating system. Whenever they say page frame, you just think about, oh, is he talking about the page frame or the physical page, right? Sometimes, they're messed up. All right, so conceptually, it looks like the picture on the right, right? So page, the page frame table, it could be an array, a page frame object. Doesn't have to be, okay? It could be a hash table, it could be a tree structure. It doesn't really matter, okay? So the operating system keep track of these page frame objects, and inside every page frame object, there's a reference to the physical page number. All right, and a bunch of other stuff. Okay, so what are the other stuff? All right, so here's an example. let's talk about the example first. We have 1 kilobytes of physical memory, okay, not the entire 4 gig, 1 gigabytes of physical memory, and we're using 4 kilobytes pages because we're running Intel, okay. So that amounts to be, right, 2 to the 18 physical pages, okay. So the page number go from 0, 1, 2, all the way to 262, 143, okay. That's 1024 times 1024 divided by 4, okay. An address, either physical or virtual, is called page align. So this is a very important word, especially when you're doing kernel 3. You're going to see this word over and over again. It's called page align if its least significant 12 bits are all 0. Okay? Because 4 kilobyte pages is 12 bits. Okay? So if all these, for physical address or virtual address, if the last 12 bits are all 0, then that address is a page align address, which means that you are accessing a memory location that is at the page boundary. Right? So that means that you're accessing either this location or this location or this location and this location and not anywhere in between. Okay? So that memory reference is called a page-aligned memory reference. Okay? Everything else, not page-aligned. Okay? So as it turns out, the reason that we have these page frame object is that it's also important to be able to perform a reverse lookup. Okay? If you have a physical page number, then you say, well, you know, which process is actually on this page? Okay, so that's really actually a really complicated question. Okay, you have a physical page frame, right? The physical page frame, you might have, 200 processes running, running in your user space. Okay, and now you have a physical page. Something's wrong with it, and you try to fix it. You say, well, which user process is using this page? Okay, so you got to be able to keep track of that. Okay, so where do you keep track of that? You can't really keep track of that in the physical page, right? Okay, because the physical page is being used by, kernel or some other processes. So that's where that information is kept inside the page frame object. Okay, so for you to do this reverse lookup, you got to have additional information inside the page frame to do the reverse mapping. Okay, so now you know that in the page frame, we have a forward mapping from that page frame to a physical page, and then the reverse mapping is mapping from the physical page back to the process that owned this page frame. Okay, and the page frame can be shared. Okay, so, the situation is actually pretty complicated inside the kernel. All right, so all these information need to be stored, inside the kernel data structure. So when you get a page fault, when you get a segmentation fault inside the kernel, you know what to do. All right. Okay. So given a physical page number, which page frame contains the information about this physical page? All right. So, in the physical, in that particular page frame, it keeps track of these pointers. But in order for you to get to that, if all you have is a physical page number, how do you get to that page frame? Okay, and again, the physical page don't have a pointer to point back to the page frame, right? So you got to have some way for you to find that page frame. Okay, and once you get to that page frame, you get all the other information about how to do additional mapping or how to make the mapping easier. Okay, but in order for you to find that, you have to go down that. I guess I'm not going to go to that slide. You got to go down to the address space representation. Okay, and maybe using additional kernel data structure to help you to find out, where that particular physical page is pointing to. All right? And then, if a page frame can be shared, then once you find that page frame, you can find all the other processes that are also using that physical page. All right? So anyways, so the situation is, what I'm trying to say is it's fairly complicated. Okay? The Unix operating system is a little simple version of that, so therefore you get to play with a simpler version of this mess. And one of the confusion that's going to come in is try to sort of really understand what is the page frame object doing. How do you go from the physical address to virtual address? How do you go from virtual address to physical address? And also the virtual address of which process? Is it the kernel process? Is it one of the user processes? How do you go from one place to another? Okay, so kernel 3, you get to play with that. All right, so oftentimes, right, when you have these mapping that needs to be done, you end up using, either sort of a tree data structure, or, in this particular case, you use a hash table. Okay? So if you use a hash table, so in reality, the page frame is not really stored in that array. It's actually stored inside of a hash table. Okay, and a hash table is something you learn in the data structure class. So I guess you take some I guess you take some information, you hash it, that will give you a bucket number, and you go to that bucket and the I guess right. I don't know if you remember a hash table. Okay, so here is the hash table. Okay, so I guess this is the hash buckets. Okay, so what you do is that you take some information about what you're looking for, you give it to a hash function. The hash function is going to generate an index into the hash table. And from that particular location, then you have to worry about collisions, right? Because many of these objects, they might hash to the same entry. So there's going to be a conflict resolution chain for all the objects that are hashed to the same bucket. Then you need to go down this data structure to find out which one is the one that you really want. Okay, so over here, again, when we try to perform a lookup, we're going to use the hash table. The hash table is going to go, is going to take you to the beginning of a conflict resolution chain. You're going to go down the conflict resolution chain to find the object that you really want, okay, by comparing what you have against what's actually stored in these objects, and eventually you're going to go to the right one. All right, so it's a very, very sort of a convoluted process for you to find mapping from one place to another. Okay, and the reason we sort of use hash table, why do we use hash table? Anybody remember data structure? Because it's fast, right? It's the order 1 performance, so they claim to be order 1. Okay, pretty good performance if the hash table is large enough. All right? Okay, so the next thing we're going to do is to sort of look at all these hardware mapping techniques. Okay, some of them are involving different kinds of hash tables, and then, different kinds of page table. So as it turns out, page table can be organized in different ways. Each one of them has their advantages and disadvantages. Okay, we're going to look through them. We're going to look at also an important data structure called translation look-aside table. Okay, that one is actually implementing hardware inside the CPU core. All right, so this is a very important picture that tells you what what a page table, what go inside a page table. All right, so we're going to replace. So remember in the previous picture when we had MMU, okay, there are a bunch of these segment register in them, base and bound, private, read-only, validity, and stuff like that. Okay. Now every one of these register, we're going to turn them into a page table entry inside the page table. Okay. So now we're using paging, right? We use the word page table. That means that every page is the same size. Okay. If every page is the same size, do you need a bounds register anymore? No, you don't need bounds anymore, right? So therefore, one of the register is gone. What about the the base register? Well, the base register. So what needs to go in here? It needs to have some kind of information about the base register. Okay. So one of these every one of these entries, if we have a page table for Intel, right, 32-bit address space over here. This is location 0. This is location 1024 times 1024 minus 1. Okay, because we can have 1 million page table entries, right? Every page is 4 kilobytes, right? So over here, inside one of these entries is that you got to remember where do they map to in the physical page. Okay, so you have a page table that contains 1 million page table entries. Every one of them is gonna, is gonna sort of simulate what we have in the segment registers. So what it needs to have is need to have the base register. Okay, and the base register in this case is a physical page number because it's a page line address, and therefore you can skip the last 12 bits and only keep the leading 20 bits. Okay, so in that case, this will give you a physical page number. The physical page number, in order to generate a physical page address, you just append 12 zeros into it, and that will give you a page line address. And then if you add any offset to it, you can address any address inside that page. Okay, so now the virtual address, 32-bit long, is going to be divided into 2 parts. Right, the first 20 bits give you the page number, but this is the virtual address, so this is a virtual page number, or this is a VPN, virtual page number. Okay, and the least significant 12 bits is used to address inside a particular page. Okay, so these two addresses are split up inside the MMU. The MMU will only look at the first 20 bits. Okay, the first 20 bits is going to be used to access one of the 1 million entries inside the page table, right? So this entire thing will go into the MMU, okay, which is a really big thing to go for the MMU to keep track of. All right, so this thing, you can imagine that this is inside the MMU. So every entry, what does it have to have? Okay, like we talked about before, every entry has to have a validity bits to say whether this entry over here or whether the rest of it is valid or not. If validity equal to 0, that means that everything else over here is invalid. If validity equal to 1, that means that, yeah, they're valid. You can use that to do address translation. The modified bit over here, it tells you whether that page has been modified or not. Okay, so if you try to write to a particular page, okay, this bit will be set to 1. Okay, if a page has never been modified, okay, then that page is set to 0. Okay, so in a way, this is kind of like the dirty bit. It tells you whether that page is dirty or not. Remember, what does dirty mean, right? If a page is not dirty, that means that this page is exactly the same as what's on disk. Okay, if page is dirty, that means that this page is not the same as what's on disk, which means that if you want to free up this page, you better copy that data onto the disk. All right, so this information is very important because you don't want to modify things in memory and then you don't write it to disk, and later on, next time when you reboot, you find out the data is not what you have. Okay, so the hardware actually keeps track of whether a physical page is modified or not. So the modified pages need to be written back to disk at some point, not right away, but at a later time. The next one is called a reference bit. Okay, it's kind of a weird bit to use. This one, it's set when the page is referenced. Okay, if this particular page is read or written to, read or write, then this bit will be set to 1. Okay, so it's kind of like the modified bit, but it's just every time you read or write, then you set this bit to 1. Okay, again, the hardware is doing this. Inside the MMU is setting these bits. Okay, this validity bit is actually not set by the MMU. It's actually set by the operating system. The operating system, when they modify the MMU register, it needs to set every one of these validity bit to equal to 0 or 1. Okay, this has happened by the M and the R bits are set by the MMU. Okay, the protection bit is the read-only, rewrite bits. Okay, that information is stored there. Okay, over here it looks like it's wider than 1 bit, because on some processor they actually distinguish between read, write, and execute. So if you want to store 3 things, then you need at least 2 bits. All right, and then the physical page number. Okay, so what about private and share? Okay, so as it turns out that information is actually not stored in the page table. The private and share, that information is actually stored inside the AS region. Okay, so it's the kernel data structure that keeps track of whether the page is private or share. Okay, so when you try to perform copy on write, all you have to do is to set this guy to be read-only. Okay, and then when you trap into the operating system, when you look up the OS data structure, that's when you realize that whether you need to perform copy on write or not. All right, so it's not part of the page table. Okay, so this is what goes into the page table entry. How big is this? Right, physical page number over here. This is, this could be, 20 bits, right? Okay, if you have 4 gigabytes of memory, this could be 20 bits. And then, 1, 2, 3, 4, so this entire entry, you probably will use, it's going to be more than 24 bits. Okay, so you will use 4 bytes to store this. Okay, if every one of these entries is 4 bytes, okay, then over here you have 1 million entry, that's 4 megabytes. Okay, so if every time when you switch to a user process, you need to load the page table for that user process in the MMU, then you got to transfer 4 megabytes of data from from main memory into the MMU. That will take a very long time. Okay, so this is, you can think of this as the conceptual representation of a page table. Okay, in reality, it's really not implemented this way. Okay, but conceptually, from this point on, when we talk about a page table, it's going to be a sort of a virtual, not a virtual page table. There's going to be a physical page table sitting somewhere. Okay, it might be broken up into, hash tables or, different kind of organization. Maybe broke down into a, hierarchy. Okay, but conceptually is that, you're going to have 20 bit in your virtual address. that's a virtual page number that will access one of these entries over here, maybe do a hash table lookup, or maybe walk down a tree or something like that. But eventually it will lead you to a page table entry, and the page table entry is what the MMU used to determine whether to generate a physical address or generate a fault. All right? Okay, so over here, right, the page table entry is analogous to the base and bound register. The base register is represented right here. The bound register, well, there's no bounds, right, because the offset is always between 0 and 4K minus 1, so it's always within bounds. All right, so what if, you have a page that you are only using part of the page, and in the end, there are places that you don't use, right, internal fragmentation. If you have internal fragmentation, what happens if you try to write to this memory location that you're not being used? Nothing. Okay, if you're allowed to write to these pages, you're allowed to write to these other places, even though, they are, you're not supposed to use it. Okay, that's another reason why it's hard to debug segmentation faults and stuff like that. It's because you might end up with a situation like this, where you're writing to memory location you're not supposed to, but when you write to it, there's no fault. Okay, and the reason for that is because we are protecting, addresses on a page boundary. Okay, we cannot protect individual memory locations to say that that location is not accessible. If you go back to the segmentation scheme, a pure segmentation scheme, where we use the base and the bound register, you can actually tell it exactly how many bytes is your segment. So as soon as you access beyond that many bytes, you can get a segmentation fault. Okay, so in that way, yes, segmentation is a little better. Okay, because as soon as you go out of bounds, you're gonna get a segmentation fault. But if you're using a paging scheme, it's not perfect. Okay, but these days all the hardware are doing paging schemes. All right, because of it's fast and etc. All right, the location of the page table. Okay, so if you don't want to store this page table in inside of the MMU, right, because it takes too long to transfer stuff in and out, so it has to be stored in main memory. So who knows where the location of this page table is? All right, so the location of the page table is part of the context of the user process or the kernel process. Okay, so you need to know where this memory location is. Okay, do you need to know the virtual memory location of this page table or the physical memory location of this page table? All right, if you know the virtual memory location, what if the validity bit for that page is equal to 0? Okay, then you can never get it back, right? Okay, if we know the base address, because we need to perform addition, using this page table entry to do some calculation, we're using pointer math, over here, add the base address to this one. If this is the virtual address, then maybe that location is not available, so you can't really access it. Okay, so therefore, eventually, what the processor needs to know is the physical memory location of the beginning of the page table. Okay, then when it can use the virtual address over here, it can compute an offset into the page table, and it will generate a physical memory reference in order to get the content of this one. Okay, so to the processor, the physical address of the page table, the first location, the first physical location to the page table needs to be known to the CPU, okay, or needs to be known by the MMU, right? Otherwise, this operation cannot be performed. Okay, so if you are storing the virtual address of the page table somewhere inside the kernel data structure, all you have to do is to make sure that as soon as you swap this process into the CPU, okay, not swap, when you switch, to run this particular process, you got to make sure that the virtual address gets translated into the physical address, and that physical address of where the page table is go into the CPU. All right, so all the CPU these days, Intel, the ARM processor or something like that, okay, inside the CPU, there's a special register that keeps track of the physical location of the page table for the current running process. Okay, for Intel, this is called the CR3 register. All right, later on, you can actually do a grep in the kernel code, look for CR3, it's in lowercase. and see if you can find it. So that's being used in kernel 3. All right, so here's the picture, telling you how things are being used, a very high-level picture. Okay, so if you have, depending on how many processes you have, that's how many page table that you need, and these page tables are stored in physical memory. Okay, so here is the process A, right? It's blue, right? It has a page table, somewhere stored inside the operating system. Process B, there's a page table for it. And the operating system, when it runs, it needs to do virtual address to physical address translation. Okay, so therefore, the operating system also needs a page table. All right, so no matter how many processes you have in the kernel, all of them share the same address space, so all of them will share the same page table. Okay, there's only one for the kernel, and then one for every user process. Okay. So the page table will point to, pages what that it belongs to. So if this is the physical memory, right, you divide it into 4 kilobytes. The green stuff belongs to the operating system will point to, the green pages, and the pink will point to pink pages, etc. Okay, and the same example of before, the user process, they can access the same virtual address location. Depends on what is being loaded into the MMU, then the right things will get performed. The right translation will get performed. Okay, so the idea over here is that what actually goes into the MMU. Okay, you don't need to take the entire, 4 megabytes of the page table into the MMU, right? All you have to do is to take a page table entry and put it inside the MMU. Okay, so out of this page table, which is 4 megabytes long, okay, how many page table entries does it have to go into the MMU? Maybe 1, maybe 2. Okay, so what happens is that these, the data inside the inside the page table is cached inside of the MMU, right? Cache means that it's a copy. So whenever you modify this guy, then you need to invalidate the cache, that kind of a cache. Okay, so over here you have page table entry over here that are cached inside of the MMU. Okay, this way is the way that you can avoid taking the entire page table and put it into the MMU, because that would be too slow. All right, so if you want to, if the ping process want to access something, okay, and if the page table entry tell you that that particular page is invalid, or you have the wrong kind of access, what's going to happen is that you're going to generate a page fault, okay, and this will interrupt the CPU, right? So now we're using paging, so this fault is called a page fault. Okay, we no longer call it a segmentation fault. Okay, so segmentation fault these days are a user level concept, right? That you access somewhere that's invalid. So once we determine that you access an invalid memory location, we call that a segmentation fault. Okay, but in the as far as the operating system is concerned or the hardware is concerned, the only fault that you can generate in this case, is the page fault. Okay, and of course there are other floating point violation, like when you divide by 0, that's a different kind of fault. Okay, but there's really no segmentation fault that really happened. Whenever you trap from the user space to the kernel space because of a memory reference, that's called a page fault. All right, so remember, page fault now include segmentation fault, and other legal faults where the operating system need to perform magic like copy on write, all right, or doing swapping and things like that. All right, okay. So this one generate a virtual address. It calls a fault. It goes into the operating system. The operating system is going to do a lot of work to try to figure out what is it that needs to be fixed. Okay, and eventually it's getting fixed, right? It find a new, in this example, if it needs to read something from the disk, allocate a spot on the physical memory to keep that data, and then fix the page table to point to the right place. So that entry, maybe no longer point to the old place, now it points to the new place. And then it will restart the operation on the ping process by returning to the user space, okay? And the next access from the user process should be a successful one. All right? So when you're doing kernel 3, what you're going to find out is that when you run the user process for the first time, is that you're gonna it's not hard to generate a page fault. Right? The hard part is actually fix the page fault. Okay? So one of the common mistakes that you're going to end up with is that you generate a page fault, you go fix something in the operating system, it returns back to the user process. The user restart that operation again, and then you trap into the operating system. Okay, and that is because something is not set up just right. Okay, if something's set up just right, if you re-access that memory location, this time it should be okay. All right, so again, that's sort of hint for you to say that, well, the last thing that you did inside the operating system, something was not set up correctly. Okay, so this picture tells you that, there's actually a lot of stuff that needs to go on to set things up correctly by allocating new pages in physical memory, adjust the page table to point to the right place, adjust the address space representation maybe, if there's something that needs to be modified. And then when everything is set up perfectly, that's the time you are ready to leave the kernel and back into the user space. All right? Okay, so we're going to, sort of stop right here. And then, Monday we're going to, pick up right from here.
This has been CS402 on Wednesday, July 9th, 2014.